everyone, this is Dr.A.Muthuselvi, Assistant Professor of Mathematics from the Standard Fireworks Rajaratnam College for Women. This presentation we will discuss about the eigenvalues, eigenvectors and its properties. So first of all, what is eigenvalue and the definition, examples. It is also we discussed the eigenvectors and its examples. Also the properties of eigenvalues. First, we define the eigenvalue. Let A be an n cross n matrix, that is a square matrix. A number, a lambda is a scalar value, is called an eigenvalue of A if there exists a non-zero vector x which is a n cross 1 matrix, that is x1, x2, etc. xn, such that Ax equal to lambda x, which is we take that element lambda which satisfies Ax equal to lambda x, means that lambda is called eigenvalue and x is called an eigenvector corresponding to the eigenvalue lambda. So next we discuss some remarks. If x is an eigenvector corresponding to the eigenvalue lambda of A, then we multiply some value alpha into x, that is alpha is non-zero number, is also an eigenvector corresponding to lambda. Next one, let x be an eigenvector corresponding to the eigenvector lambda of A, then Ax equal to lambda x, so that we take the left side from right side, Ax minus lambda x equal to 0. Also we take x from the outside, that is A minus lambda into x equal to 0. Hence here the product of two elements equal to 0 means also x is not equal to 0. So we get modulus of A minus lambda I equal to 0, which is the characteristic polynomial of A. Let modulus of A minus lambda I equal to some polynomial A naught into lambda power n plus A1 into lambda power n minus 1 plus etc. an. The roots of this polynomial gave the eigenvalues of A. Hence eigenvalues are also called characteristic roots. So next we discuss the properties of eigenvalues. First one is any square matrix A and its transpose A dash have the same eigenvalues. That is lambda is the eigenvalue of A, means that lambda is also an eigenvalue of A dash. First of all we take A minus lambda I the whole dash, which is equal to, we know the property A plus B the whole dash equal to A dash plus B dash. So here A dash minus lambda into I dash. Lambda is a scalar value, so we cannot take lambda dash, which is equal to A dash minus lambda into I. So identity matrix I dash equal to I also. So here take the modulus in the left side and right side. Next A minus lambda I the whole dash equal to A dash minus lambda into I, which implies modulus of A minus lambda I equal to A dash minus lambda I. We know that A minus lambda I equal to 0 if and only if A dash minus lambda I which is also equal to 0. Therefore, lambda is an eigenvalue of A if and only if it is an eigenvalue of A dash also. Next one, the eigenvalue of a triangular matrix are just the diagonal elements of the matrix. So we take any triangular matrix. Here we take upper triangular matrix, that is A11, A12, A13, etc. A1n. Next 0, A22, A23, etc. A2n, etc. Last row A00, etc. ANN, which is equal to 0, is a triangular matrix of order n. Next we find modulus of A minus lambda I, which is equal to A11 minus lambda, A22 minus lambda, etc. ANN minus lambda. So next we find the roots of A minus lambda I, which is equal to 0, which implies lambda values are A11, A22, etc. ANN. So hence the eigenvalues of A are the diagonal elements of A, that is A11, A22, etc. ANN. From this property we have a corollary, that is the eigenvalues of a diagonal matrix are just the diagonal elements of the matrix. The third property is, let X be an eigenvector corresponding to the eigenvalues lambda 1 and lambda 2. That is, an eigenvector contains two types of eigenvalues, means that two are equal. By the definition, x is not equal to 0, we know that. So next, Ax equal to, by the definition of eigenvalues, Ax equal to lambda 1x and Ax equal to lambda 2x. Here left side are equal, so right side are also equal. That implies lambda 1x equal to lambda 2x, which implies lambda 1 equal to lambda 2. That is, all them eigenvector have only one eigenvalues. Fourth property is, the sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. First of all, we take a square matrix. Here 3 rows, we take 3 cross 3 matrix. A11, A12, A13, A21, A22, A23, A31, A32, A33. Next we find modulus of A minus lambda I, which is equal to A11 minus lambda, A12, A13, A21, A22 minus lambda, A23, A31, A32, A33 minus lambda. Next, we simplify that determinant value. We have modulus of A minus lambda equal to minus lambda cube plus lambda square into A11 plus A22 plus A33 minus K1 lambda plus K2. Here first we take the values of lambda power 3 and lambda square. Next we take lambda and the remaining coefficients is taken to be K2, where K1 and K2 are expressible in terms of the element Aij, where I equal to 1 to 3 and j equal to 1 to 3. If lambda 1, lambda 2, lambda 3 be the eigenvalues of A, since here we take the square matrix of value 3, so we have 3 eigenvalues. Let it take be lambda 1, lambda 2, lambda 3. So next we find A minus lambda equal to minus 1 the whole power 3, my lambda minus lambda 1 into lambda minus lambda 2 into lambda minus lambda 3, which is equal to minus lambda power 3 plus lambda square into lambda 1 plus lambda 2 plus lambda 3 minus k3 into lambda plus k4. So we take only 3 values, where k3 and k4 are expressible in terms of the elements lambda k equal to 1, 2, 3. We substitute these values. We take only the coefficients of lambda square. We get lambda 1 plus lambda 2 plus lambda 3, which is equal to a1 plus from 3 and 4 we take lambda 1 plus lambda 2 plus lambda 3 equal to a11 plus a22 plus a33. So we get the sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. Next property is the product of eigenvalues of a matrix A is equal to its determinant. So we take the same square matrix A, so we have 3 eigenvalues. Let it be lambda 1, lambda 2, lambda 3. Then A minus lambda equal to minus 1 the whole cube into lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda 3. It take from the previous equation, previous remark 2, that is a naught into lambda power n plus a1 into lambda power n minus 1 plus etc. an. Here we take only the coefficient of a n minus 1. So we substitute lambda equal to 0 in equation 5, we get cardinality of modulus of a equal to k4 only. So where k4 is expressible in terms of elements lambda k, where k is equal to 1, 2, 3. Next property is, if lambda is an eigenvalue of a matrix A, then 1 by lambda is an eigenvalue of A inverse. First of all, we take let x be an eigenvector corresponding to lambda. Then by definition, Ax equal to lambda x. Pre-multiplying both sides by A inverse, we take A inverse into Ax equal to A inverse into lambda x. That is, A into A inverse means I. So I into x equal to A inverse into lambda x. We take the lambda from the outside, that is x equal to lambda into A inverse x, which implies A inverse x equal to 1 by lambda into x, which is also a definition of your eigenvalues. So that 1 by lambda is an eigenvalue of the inverse matrix A inverse. Next corollary, if lambda 1, suppose we take n eigenvalues, means lambda 1, lambda 2, etc. lambda n, then A inverse have the eigenvalues 1 by lambda 1, 1 by lambda 2, etc. 1 by lambda n. Next property is, if lambda is an eigenvalue of A, then k into lambda is an eigenvalue of k into A, where k is a scalar. Let x be an eigenvector corresponding to lambda, then by the definition of eigenvector Ax equal to lambda x, we multiply k on both sides, we get k into Ax equal to k into lambda x, that is k into lambda into x. Therefore, k lambda is an eigenvalue of Ka. Next property is, if lambda 1, lambda 2, etc. lambda n are eigenvalues of your matrix A, then A power m has eigenvalues lambda 1 power m, lambda 2 power m, etc. lambda n power m, where m is a positive integer. So, first of all, we take lambda I be an eigenvalue of A and xi be the corresponding eigenvector, then A into xi equal to lambda I into xi by using the previous properties. Next, we pre-multiply by A, we get A into Axi equal to A into lambda I xi, which implies A square into xi equal to, we multiply lambda I into Axi, which is equal to lambda I square into xi. Similarly, we get A power 3 xi equal to lambda I power 3 into xi. In general, A power m xi equal to lambda I power m xi. So, here we have lambda I power m is an eigenvalue of A power m. So, first in example, we take a square matrix of order 2, A equal to 1, 2, 3, 4. So, first step is we have to find the determinant of A minus lambda I. So, which is equal to 0. So, we substitute the values of A lambda. So, which is equal to lambda minus 2 into lambda plus 5 equal to 0, that which implies lambda value is equal to 2 or minus 5. So, next step, we have to find the eigenvector corresponding to the eigenvalue lambda 1 equal to 2. So, here we take A minus lambda I into V equal to 0. V means the vector V1, V2. So, here the order is 2. So, we have to take 2 vectors V1, V2. So, we substitute the value of A minus lambda I into V, which is equal to 0. Here we take the value lambda equal to 2. So, first vector which is equal to minus V1 plus 2 into V2 equal to 0, 3V1 minus 6V2 equal to 0. We have to find the values of V1, V2 from these two equations. We have V1 equal to 2, V2 equal to 1. Also, we find the two eigenvectors corresponding to the eigenvalue lambda 2 equal to minus 5. Next example, we have to take the three square matrix of order 3. So, first step is compute modulus of A minus lambda I. So, which is equal to 3 minus lambda into minus lambda into 2 minus lambda. So, which is equal to, we take which is equal to 0. So, first eigenvalue equal to 0, second one is 3 and the third one is 2. So, next we find the 3 eigenvectors corresponding to these eigenvalues. So, first we take lambda 1 equal to 0. So, we here in this case we have the eigenvectors values which is equal to x1, that means x1, x2, x3 equal to minus 10, 3 into 3, 1, which into s. S means which belongs to a real number or. Thank you for watching this video. We will meet in the next video.